Welcome to another session on system software. Myself Meenu Matthew. I'm an assistant professor in computer science and engineering at Rajagiri School of Engineering and Technology. In this session, we'll be talking about the two-pass assembler and the hand assembly of SIC and SIC XC programs. Okay, let's start with the first topic, a two-pass assembler. As you have already seen in Module 1, an assembler is a program or a software that is used to convert a program that is written in assembly level language program into a machine code. Now here the machine which we consider here is SIC and SIC XC. So we will be converting a program that is written in SIC or SIC XC into its corresponding opcode. And this particular machine uses hexadecimal opcode. Instead of binary, we use hexadecimal opcode. So we have split the assembler into two parts. I mean, the assembler has two halves, the pass 1 and pass 2. It parses the program twice. During the first pass, the source code is given as the input, and the source code is parsed once to see the symbols that are used in the program. For all the symbols that are used in the program, we make an entry in the sim tab, and also for each instruction we record the location counter value. Okay, so these are the data structures which you have learned, and we are going to populate it during the pass 1. After each line is parsed in pass 1, it is written into an intermediate file. Okay, and this intermediate file will serve as the input to pass 2. So pass 2 has the source code from intermediate file as input, and it gives the object program as the output. The object program is nothing but the opcode in hex, and it is written in terms of header record, text record and end record. This you might have already studied. Why do you need a two-pass assembler? Why don't you convert the code directly at once? The reason is forward reference. As you can see in the example, the program name is copy and it starts at location 1000. The first executable line is at 1000 and the instruction is STL return address. Okay. After conversion, you get the code 141033. But at the very beginning, the assembler, when it encounters this particular statement, STL's opcode is available at op tab, which is given by the assembler itself, and return address does not have an address as of now, because it is the first time that you encounter the simple return address. But it has a definition at line number 95 with the address 1033. That is what you see here. Now, how do you keep track of symbol addresses? That is where the data structures come into use. We have to store return address into the symbol table with the corresponding address 1033. So as and when there is a call to a particular symbol, you can directly look up the symbol table and get its address. Now this reference is called a forward reference because you refer to a symbol which is not yet defined. Now before we move on to the algorithm, let me introduce you to the three columns of a program written in SIC or SIC XC. Now the first column is the label field, where you can see the symbols, and if you encounter a symbol in the first field, then it is a symbol definition, which means you have to enter that symbol in sim tab. For example, the encounter of first means you have to enter first into symbol table with address 1000. C loop has to be entered into the sim tab with address 1003. And how did you get 1003? It is 1000 plus the length of STL return address, that is 3. 1000 plus 3, 1003. And it goes on. And if a particular instruction has length 4, it becomes 1000 plus 4 or 1003 plus 4. Okay. And the second column is the mnemonic opcode. In this column, you can see all add, LDA, STA, LDCH, RSUB, JSUB, all those things. The code for all the mnemonic code is available in op tab, and it is given by the assembler. Then the last field or the third field has the operand, that is the operand of the instruction. It is a symbol and its address will be available in sim tab after first pass. Now let's look into the algorithm of two-pass assembler. We'll begin with pass 1. Now in pass 1, we'll traverse the program once, find all the symbols, enter it into SimTab. That is our purpose. So we will start with the first line, read the first input line, and if you see the opcode as start, that is a middle field, has the assembler directive start, then save hash operate, meaning the number which comes immediately after start has to be taken as the starting address. So if it is copy start 1000, you take 1000 as the starting address. Initialize location counter to starting address. We have already seen this in the example. Now write the line to intermediate file and read the next input line. Now that you have got the starting address, you have nothing else to do with the start statement. You can simply write it into the intermediate file and read the next input line. Now what if the first the start directive does not have an operand next to it? Then you can initialize the location counter to 0, meaning the default starting address is 0. We are done with the start statement or the start assembler directive. Now we'll move on to the second line. What has to be done? For all the lines coming after start till end, we will have to convert it into the machine opcode. Begin. If this is not a comment line, we don't have to deal with comment lines. It can be ignored. Then if it is not a comment line, then see whether there is a symbol in the label field. Label field is the first column. So if there is a symbol, it means it is a symbol definition. So if you obtain a symbol definition, that has to be kept in symbol table for future reference. So we will search the SimTab for the label which we got. If it is already there, what does it mean? It was encountered before, it already has an entry, we don't have to duplicate. Set an error flag saying it is a duplicate symbol. Else, if it is not there, make a fresh entry with the label and the corresponding location counter into the symbol table. Okay, the location counter is nothing but the value which you saw in the previous slide on the left of each instruction. Then now we are done with the first column. Now we'll move on to the second column of the program. The second column of the program has a mnemonic opcode. Now what are the options or what are the possible mnemonic opcodes which can come in the second field? We'll start one by one. Search optab for opcode. If found, that is if you find the opcode there, this is for all the standard instructions. Standard instructions meaning the STA, LDA, LDCH, add, sub, RSUB, JSUB, all those things, all those regular expressions, all those regular opcodes has instruction length of 3 and that can be added to the location counter to get the next address. Okay, that is what we did. 1000 plus 3, that makes it 1003 in the previous slide. Now the other option, other than all these, the next possible word that can come is word, W-O-R-D, which means it is an integer constant. Integer constants take 3 bytes of space, so we will have to add 3 to the location counter. Now the next option is reserve word. Reserve word is reserving 1 word space, and 1 word in SIC or SICXC is 3 bytes. So we will be reserving 3 into the number specified. So if we reserve 6 words, reserve word 6, we will have to multiply 6 by 3. So it is 18 bytes. So add 18 to location counter. I just give you an example. Now the other possibility of opcode is reserve bytes. Okay, if it is reserve bytes, it will be followed by a number, which means that many bytes has to be reserved. So you have to simply add hash operand to the location counter. Now the next possibility is a byte. Byte is an assembler directive which indicates a hexadecimal constant or a character constant. Be it hexadecimal or a character constant, you have to find the length of the constant in bytes, add it to the location counter. That will give you the next location counter address. Now what happens if it is none of this? If it is none of this, it means the user has written something which does not belong to the instruction set of the machine. So it is an error. You can flag the error and say that it is an invalid operation code. This goes on for all the lines of code till you encounter end. After each line is checked for one of the opcodes, we have to write the line to intermediate file as such without any other modifications. And we read the next line, check whether it belongs to one of these valid opcodes. If it is valid, we add the corresponding instruction length to the location counter, else we'll flag an error. Now this is done till end, and the last line is written explicitly to the intermediate file. Now the next line, save location counter minus starting address as the program length. Obviously, the last location counter minus the first address would be the length of the program. This is needed for populating the header record in the output format. You might have already studied. The header record has the symbol H followed by the starting address, length of the program, and that length has to be taken from this. Now the source code is available in intermediate file. Symbol table is complete. Location counter values are found out. Now we'll begin pass 2. In pass 2, we'll convert each line into its corresponding machine code. As in the example, we saw 141033. That code is generated from pass 2. Okay, let's begin. We'll read the first input line. Obviously, it is from the intermediate file. Then, if the opcode is start, the first line obviously has a start assembler directive. If it is start, we simply write the listing line and read the next input line. Listing line is nothing but a metadata about the program. It will have the user who has created, the last change that was made, what was the change, what is the opcode, all these things. All the general data about each line would be associated with the object program. Now, write the header record to object program. The header record is all ready because from pass 1 we have got the length of the program. So header record is ready, that is written out to the object program. Now we'll initialize the first text record. As you all know, the program can contain multiple text records. So we'll begin the first text record. Now, while the opcode is not equal to end, that is till the end of the program, we are going to convert each line into its corresponding opcode. If this is not a comment line, because we are not bothered about the comments, search optab for the opcode. See whether it is a valid opcode. If it is valid, retrieve its machine equivalent from the optab. Optab is directly given by the assembler. Now, if it is found, then see whether there is a symbol in the operand field. That is, you got a value for the mnemonic opcode and see whether there is a value to the right. There is an operand. Now the operand would be a symbol, and all symbol and its corresponding addresses are there in symbol table. Now we go to the symbol table, search for the operand. If it is found, store the symbol value as operand address. If it is there in symbol table, it will contain an address stored in the symbol table, and you can use that address as the operand address. Else, if you don't find the particular symbol in the symbol table, it means the operand is missing. So you can store 0 as the operand address and flag an error saying it is undefined symbol. That is, you are using a symbol that is not defined. That is why it was missing in symbol table. Then there is another possibility that a particular instruction does not have an operand, like RSUB, return subroutine. It does not have an operand. So what has to be done? In order to fill the instruction format, you can fill it with zeros. Store 0 as the operand address. Then assemble the object code. Now you have got the opcode from optab and the operand address from the symtab. You can assemble them. That is, 14 is obtained, 1033 is also obtained. You can assemble them to form the actual opcode. Then if the opcode is byte or word, which means it is a constant, hexadecimal constant or a character constant, then convert the constant to object code. Now, if the object code does not fit into the current text record, a text record normally can contain 10 to 12 object codes, instruction codes. If a particular instruction code does not fit into one single text record, you cannot split it into half. Instead, you have to move the entire thing into a new text record. Okay, write the text record to a new to object program and initialize a text record. That is, the text record in which you were writing till now has to be moved to the object program and you have to initialize a new text record. Then add the object code to the text record. That is, add the that is, if it does fit into the current text record, you can add it to the text record. Once it has been written into the object program, you can write the listing line and read the next input line. This is done for each and every line till you encounter end. End is an assembler directive. It does not have to be converted. Now, at the end, once you complete translating all the lines, the last text record would be in your buffer. You can transfer it to the object program, write the end record and the last listing line and stop. There ends pass 2, and the output of pass 2 is an object program which has the header record, text record and the end record. In the previous session, we saw how does an assembler convert a machine level language program into opcode. Now we'll do the same using pen and paper. We'll convert an SIC program into its corresponding opcode. As in the example, we saw 141033 instead of STL return address. Likewise, we'll find the opcode for each and every instruction that you see on the screen. The given program has the name as sum and it starts at location 0. Now before we start converting, for each and every line, we have to recollect the addressing modes that we learned in first module and the instruction format of SIC and SICXC. Okay, now let's begin with the first statement, LDX #0. From the very instruction, we know that we are going to load the number 0 into the register X. So #0 indicates that it is immediate addressing, that is immediate operand is given there. Now the address for storing LDX is the address 0. Why? Because this is the first executable address and the executable address is 000 as we have obtained from start statement. Then the length of LDX #0 is 3. Okay, so what happens? The next instruction LDA #0 will begin at 0000 plus 3 0003. Okay, now LDA #0 again is an immediate addressing where the accumulator is loaded with the number 0. Its length is 3. So the next instruction will begin at 6. Now coming to the next instruction is this plus LDB. The symbol plus there indicates that it is format 4, meaning the length of the instruction is 4 bytes instead of 3 bytes. So the length is 4. So the next address should be 0006 plus 4. Okay, there is a tricky part there. Coming to the next one, the base used in the program is table 2. That is the address for table, the address of table 2 is used as the base address. Since base is an assembler directive, it does not have to be stored. It is just an instruction to the assembler. Now coming to the next one, the next instruction add table comma X is at A. Why didn't we write 10 there? Because it is hexadecimal. When we add 6 plus 4, we get 10, but do not write 0010. It is wrong. Instead, you have to write 000A. Then add table comma X has length 3 bytes. So the next instruction is A, B, C. The next one is D. Okay. So add table comma X is begins at A and is stored from A to C. So the next instruction will begin at D. Next instruction is add table 2 comma X. It has the length 3 bytes. So D plus 3 is D, E, F. The next one is 10. I hope it's clear. Now ticks count is 3 byte instruction. So we'll add 3 to it. So the next one, the next address is 13. The next instruction is JLT loop. It has a length 3. So what should be the next location counter? It should be 1, 3 plus 3. From the previous slide, the next location counter value is 0016, that is 0013 plus 3. The current instruction to be processed is plus STA total. Plus indicates format 4, so the length is 4. So 6 plus 4 is 1A instead of 20. Okay, now RSUB is a 3-byte instruction, and we add 3 to 1A, it makes the location counter 1D. Again, it is a 3-byte instruction, we add 3 to 1D, which makes it 0020. Now, table reserve word 2000. So what would be the size? According to our algorithm, reserve word will reserve as many words as described after it. So 2000 into 3 words would be reserved, that is 6000 bytes would be reserved. So instead of writing 6000 bytes as length, we have to write it as 1770. This is nothing but 6000 in hex. Now adding 1770 to 0020, we get the next address as 1790. Again, table 2 reserve word 2000, it is 6000 bytes in decimal, but in hex it is 1770. So adding the location counter and length, we get the next address as 2F00. Now total reserve word 1 will reserve 1 word, and that is 3 bytes. So it makes the last address as 2F03. Now we've kept all the location counters ready. We'll start converting each line into its corresponding opcode. Now before we start converting, let me introduce two terms. The first one is target address. Target address is nothing but the address of the operand. For example, if you take STL return address, the address of return address is the target address. Then the program counter, it is nothing but a variable that stores the address of the next instruction to be executed. For example, if you are at line number 2, your program counter will contain the address of line number 3. Now we'll begin with LDX #0. It is of format 3. So I've drawn the instruction format for format 3. These are the addressing modes, NIXBPE. Since it is immediate addressing, I can put I as 1 and N as 0. Indexed addressing will never occur with immediate addressing, so indexed addressing X is 0. Then since it is format 3, E bit is 0, B and P are 0, because relative addressing can not be used here. Now LDX has the opcode as 04. In terms of hexadecimal, it is 000001. But our opcode can be represented only in 6 bits. So the last 2 bits can be ignored. So we'll write 00001. Now, what has to come here? A 12-bit displacement. But here we don't have a displacement. Instead, we have to put the immediate operand. Immediate operand is 000, complete zeros. So in effect, how do you write the opcode for LDX #0? Group in bits of 4 from the left or right and write its corresponding hexadecimal. So here it is 0, 5, 0, 0, 0, 0. So that makes the opcode 0540. Now coming to the next one, it is LDA #0. Again another format 3 instruction. We'll draw the instruction format for format 3, NIXBPE. It is immediate addressing. So I is 1, N is 0, X is 0, E is 0, B and P are 0. Same as before. Now LDA has the opcode 00. It is written as 8 zeros. We'll ignore the last 2 and put it in opcode field. Now what has to come in the displacement? The next column, the immediate value, that is 0. So that makes the opcode 010. How did you get this? 0, 1, 0, 0, 0, 0. Okay. Third instruction is plus LDB table 2. When there is a plus sign at the beginning, it means it is format 4. In format 4, instead of a 12-bit displacement, you have a 20-bit address over here. Okay, now since it is hash table 2, it means it is immediate addressing. So I is 1, N is 0, X is 0, E is 1 because it is format 4, and B and P are zeros. Now LDB has the code 68. We'll ignore the last two, write the rest in the first column. 68. Now in place of the 20 bits, I have to write the address of table 2. From the slide where you have found out the location counters, you can see table 2 has the address 1790. I've added 4 zeros at the beginning to make it a 20-bit address. That makes the code 69101790. Okay, so 1, 2, 3, 4 bits. Sorry, 4 bytes. Fourth instruction is add table comma x. Since there is an x in the instruction, it means index register is used. Table is an array, and you are addressing the xth index of the table. So we'll draw the format for format 3, NIX BPE. Since it is indexed addressing, N and I are 1. Okay, we use the value for N and I for symbol addressing. So indexed addressing, it is 1, E is 0 because it is format 3, and by default I assume that it is program counter relative addressing. There are situations when we go with base relative addressing. We'll come to it later. Now the addressing bits are ready. Now add has the opcode 18. We'll ignore the last two, write the rest in the first column. It is 0001 10. Now in place of the 12-bit displacement, we should find a displacement that is given by the target address minus program counter. Here the target address is the address of table from the first slide, and the program counter will contain the address of the next instruction. So this is add table comma x. So program counter will contain the address of the very next instruction. So it is 0020 minus 000D. It will give you 0013. Since we can only represent 12 bits here, we'll ignore the leftmost 0 and put it in the 12-bit displacement column. So that makes the opcode as 1BA013. Next instruction is add table 2 comma x. Like the previous one, here there is another x, which means you're indexing some array. Here the array is table 2 and it uses format 3. Now I is 1, N is 1, X is 1. Then E is 0 because it is format 3. For B and P, I'll put B as 0, P as 1. Then add as 18. We ignore the last 2 bits, put the rest in the first column. Now in place of the 12-bit displacement, we have to find the displacement, and displacement is given by target address minus program counter. So it is 1790. That is address of table 2 minus program counter is the address of the very next instruction after add table 2 comma x, that is 0010. When we subtract, we'll get 1780 in hex. If you remember, in the previous instruction, it was 0013. We could ignore the last the leftmost 0, but here there is something tricky. It means it is already a 16-bit displacement that cannot fit into this particular column. So in decimal it is 6016. It is a bigger displacement. So I have to change my assumption that it is program counter relative addressing to base relative addressing. So the new displacement is target address minus base. It is 1790 minus base's address of table 2 itself, 1790. It makes the displacement 0. So what should happen? P and B has to be interchanged. P to 0 and B to 1, and put the displacement as 0. So the opcode becomes 1BC000. Now TIX count is a 3 byte instruction. So we'll draw the format for format 3. NIXPPE, I is 1, N is 1, indexing is 0 because there is no X here. The X in TIX does not refer to indexed addressing. Then E is 0. By default, I assume program counter relative addressing. TIX has the opcode 2C. So I'll ignore the last 2 bits and write the rest in the first column. Then displacement is target address minus program counter. Here it is 00A. Okay, and the opcode becomes 2F200A. The next instruction is JLT loop. Again another format 3. I is 1, N is 1, X is 0 because there is no X in the instruction. E is 0, B is 0 and P is 1. By default, we'll always go with program counter relative addressing. Now TIX is 38. We'll ignore the last 2 bits and write the rest in the first column. Now we have to find a displacement for the last column. So displacement is given by target address minus program counter. Here the program counter is greater than the target address. That is why you get FF here. If you look into the calculator, you can see a set of F followed by 4. So you can ignore the F. The F just means that it is a negative number. The value is actually minus 12. So you can write FF4 in the displacement column. So that makes the opcode 3B2FF4. The 8th instruction in the program is plus STA total. Since there is a plus, it means it is format 4. This is the instruction format. I is 1, N is 1. Since there is no X, X can also be put as 0. Then E is 1 because it is format 4. Now B and P. Since we need an address in place of the displacement as in format 3, in format 4 we need an address. So the relative addressing will never occur here. Okay, so it is 00. STA is 0C. So we'll ignore the last 2 bits, write the rest in the first column. Now in place of the 20-bit address, we have to write the address of total. So total has the address 2F00. So that makes the opcode 0F102F00. The last instruction in the SIC program was RSUB. It is followed by all declarations, the data declarations. So this is the last instruction that has to be converted. It is a format 3 instruction. So N is 1, I is 1, X is 0, B and P are zeros, and E is 0 because it is format 3. And if you remember, RSUB is one instruction which does not have an operand. Okay, so RSUB is 4C. Ignoring the last 2 bits, we can write the rest in the first column, and in place of the 12-bit displacement, I've put all zeros because it does not have an operand. So it is zeros. That makes the opcode 4F followed by 4 zeros. Now that you have studied the hand assembly of SIC XC program, it would be much easier to convert SIC programs. Since in SIC XC program there are only 2 addressing modes, one is direct, another one is indexed. So if it is direct addressing, the addressing bit is 0, and if it is indexed addressing, the addressing bit is 1. So this is comparatively easier. We'll move on with the same example, sum. There is some difference in the statements. It starts at location 4000. So the first location is 4000. And the length of all instructions in SIC is 3 bytes. There is no change. There is only a change for the reserve word in the example. So here the length is 3. So the next instruction is 4003. LDA 0 is at 4003. It has the length 3. So add table comma x will begin at 4006. Again another 3 byte instruction. 4006 plus 3 is 4009. Again another 3 byte instruction. It makes 400C plus 3 will give you 400F. Another 3 4012 4015. Now here is the tricky part. It is table reserved 2000, which means 6000 byte has to be reserved. As we saw in the previous example, we have to add 1770. After adding 1770 to the previous address, we'll get the address of count reserved 1 as 5785. Length of current instruction is 3. So the address of next instruction is 5788. Another 3 byte instruction. So the next instruction begins at 578B. Again another 3 byte instruction. So the last location is 578E. We'll start with the first instruction, LDX0. This is the instruction format for SIC. There is an indexing bit X. Since there is no X in the instruction LDX0, it is direct addressing, so X is 0. LDX has the value 04. Since here we use an 8-bit opcode, you do not have to ignore anything. You can write it as such. The code for LDX can be written as such. Now target address of the operand. Here the operand is 0 and the target address is 5788. So 5788 has to come in the third field. But the third field can contain only 15 bits. So we'll ignore the leftmost 0 and write 101, 0111, the rest. Okay, so that makes the opcode 045788. Now LDA 0. It is again the same instruction format with the X value as 0. LDA has the opcode 00. It can be straight away written in the first column. And the target address of 0, as we saw in the previous slide, it is 5788. That can be written here. Since it is 15 bits, we ignore the leftmost 0. Write the same thing, ignoring the leftmost one. So opcode is 005788. Add table comma X. Again the same instruction format. Here you can see an X here, which means it is indexed addressing. So X value is 1. Add has the opcode 18. It can be straight away written into the first column. And the target address is the address of table. Address of table is 4015 from the location counters. Write it ignoring the leftmost bit. So opcode is 18C015. Next instruction is ticks count. The addressing mode X is 0 here because it is not indexed. Now ticks has the value 2C. It can be straight away written in the first column. Now the target address that has to be used here is the address of count. Count has the address 5785. We'll write it by ignoring the leftmost bit. Okay, only 15 bits can be included in the third column. So the opcode becomes 2C5785. JLT loop. Again the same instruction format. X value is 0. JLT has the opcode 38. It is straight away written in the first column. And the right column has to have the target address of loop, which is nothing but 4006. Again it is written in 15 bits. So the opcode is 384006. STA total. Here the indexed addressing is 0. STA has the value 0C and total has the address 578B, which is written in the next column, and the opcode becomes 0C578B. Now you'll obtain the opcode by grouping it in groups of 4 bits. Next one is RSUB. X value is 0. RSUB has the opcode 4C. It is written in the first column. And since there is no operand, we'll put the 15 bits as zeros, which makes the opcode 4C followed by 4 zeros. The last, after the RSUB, you can see some assembler directives like RSW, RESB, etc. Those things do not have a conversion. And if you observe, there is a 0 word 0 there, which is a integer constant that has to be represented in the opcode as 000000. If it was 5 word 5, you would have written 000005. That is all about the session. Thank you for your patient listening. Thank you.